dear learner, good morning to all. I welcome you all to this module on fundamental and advancement of wind energy resource assessment. After this learning module, you will be able to predict the accurate wind resource for a particular site. You will be able to reduce the uncertainty available in the time series wind data. You will be able to optimize the design of wind turbine, and you will be also be able to reduce the cost of electricity production. That means a unit cost of electricity. Additionally, you will be able to explore the new research areas in the area of wind resource assessment and deployment and development of wind energy technology. The energy extracted from the motion of air results in wind energy. The uneven temperature distribution due to the solar radiation and earth rotation are the two main cause of air motion or wind. We all know that wind energy is a renewable, non-conventional, inexhaustible and non-polluting source of clean energy. It has no adverse effect on the environment, and it also avoids fuel provision and transport. Therefore, it is going forth as a fast emerging, developing and popular alternative source of energy, which can also be called as a source of clean energy. As a source of power, the potential of wind energy is huge globally. In India, we also have an immense amount of wind power. India has a huge wind resource potential, but it requires an accurate assessment, most particularly at higher heights as well as in hilly and complex and mountainous region. The modern wind turbine or machines are becoming bigger and higher, reaching to the unknown turbulence and wind regimes in the atmosphere. Therefore, it is essential to assess the availability of wind resource before starting or deploying the wind power project. In terms of atmospheric characteristics, which may generate turbulence, power production and for a successful return on the project investment. The efficient use of wind energy require exact, accurate and precise wind measurements. The wind resource assessment plays a significant role in successful development of wind power. The detailed, accurate and proper wind resource assessment, particularly determining the characteristics of wind, that is wind speed, wind direction, it is very necessary for proficient planning, implementation of any wind engineering farm project and to increase the efficiency of wind energy market. Additionally, it will also help in reducing the cost of power generation and most optimum and most important the selection of wind energy conversion machine, or we can say that wind turbine. First of all, we should know what is wind resource assessment. It can be understood as the process of evaluating or determining or calculating the energy potential that can be harnessed from wind in a particularly geographic area. This wind resource assessment is a crucial step in determining the feasibility and viability of wind energy project such as wind farm or individual wind turbines. Overall, wind resource assessment is a multidisciplinary process that combines the field of meteorology, statistics and engineering analysis to provide critical information for decision making in wind energy project. Accurate assessment lead to informed choices about turbine placement, about the finance of project and the feasibility of overall wind energy project. Now, the wind energy resource assessment technique can be classified into two types. First one, we all know the traditional technique or a tower based technique or a meteorological mast technique or a conventional techniques. Second is the upcoming and the most advanced technique is remote sensing techniques, which consist of remote sensing instrument, unlike in the traditional technique. First of all, now we will discuss the traditional techniques and what are the equipment that is used in a traditional technique. The traditional techniques or tower based techniques or a meteorological mast technique uses a high lattice tower or a tall meteorological mast equipped with a various sensors for the measurement of various parameters. It is a stand-alone and a point measurement techniques which is used worldwide from a several past decade. Using common cup anemometer for measuring wind speed, and for measuring the wind direction we uses wind vanes, and there are different temperature and pressure sensor which are used to measure the temperature and pressure. The cup anemometer assembly, basically it consists of 3 or 4 cup. It is centrally connected to a vertical shaft for rotation. In this cup anemometer, at least one cup always faces the upstream wind. The aerodynamic shape of the cup converts wind pressure into a rotational torque. A transducer inside the anemometer convert this rotational movement into a electrical signal, which is further sent to a data logger through a wire. Similarly, it always remains in a position of a equilibrium by aligning itself in the direction of wind. For measuring the wind direction, we uses a wind vane, which consists of a potentiometer type transducer that outputs an electrical signal relative to the location of the vane. Further, this electric signal is transmitted by a means of wire to a data logger and relates the vane position to a known reference point, and this known reference point usually and generally we take as north direction. The flow of air near the anemometer is significantly affected by the mast used in the wind resource assessment. This effect is known as tower shadow, and it becomes pronounced when the anemometer is in a wake of the mast. Here we have used one term wake, which will be learned in the another module. This tower shadow effect can be reduced by selecting the higher reading of a 2 anemometer at each height as the value of measured wind speed for each averaging period. The meteorological mast measurement is rarely located precisely where wind turbines are constructed. It cannot be moved once constructed. Cup anemometer are fixed and it is static, only measures a relatively small fixed point at a time, and it is not capable of measuring the complete area utilized by the wind turbine blade, as we have seen that wind turbine blades are very huge and they are very long. Therefore, the meteorological mast has one of the major advantage that it only measures the point data. It gives only a point measurement. So, next we move on to the key components and methods which are involved in the wind resource assessment. There are several key components which are wind data collection, data analysis, wind speed frequency distribution, Weibull distribution and parameters, wind resource mapping, wind energy yield estimation, wind farm layout and micrositing, uncertainty analysis, validation and calibration. Now, let us discuss each one by one. First, wind data collection. By the help of cup anemometer, we collect our wind data, and by the help of wind vane, we collect or we record the data of wind direction. Similarly, through various sensors, we record the data of temperature and pressure. So, this wind data collection is a very important and plays a significant role in development of wind energy power plant. So, wind data collection begins with collecting the reliable wind data. This is usually done using a meteorological instrument like cup anemometer and wind vanes in traditional measurement techniques. This data collection can take place over a period of months or years to capture the variability of wind patterns. Now, second is a data analysis. Once we have collected the wind data, next it is analyzed to understand the behavior of wind, that is wind speed, direction, frequency distribution. Next we do analysis with the help of statistical method, which is used to identify the average wind speed and the average wind direction, the trends of wind direction and variations over a different time scale. This time scale can be taken as hourly, seasonal, annual or 10 minutes average time series wind data. Third one is wind speed frequency distribution. This wind speed frequency distribution is often represented as an histogram or a probability density function, provides an insight into the likelihood of encountering different wind speeds at the assessment site. This distribution helps us to estimate the wind production of a site with the help of or a potential of wind turbine. Fourth one, Weibull distribution and its parameter. The Weibull distribution is commonly used to model wind speed probability distribution. The two important parameters of a Weibull distribution are shape factor and a scale factor. Weibull distribution are determined from the collected wind data and are used to estimate the long term average wind speed and its variability. Fifth one is wind energy yield estimation. Wind resource assessment calculates the potential energy production of wind turbine based on the assessed wind speed. This estimation is crucial for determining the economic feasibility of wind energy project. The economic feasibility of a wind energy project is very important because while developing a wind energy project, a huge investment is required. Now, sixth is wind resource mapping. The geographic information system are used to create a wind resource map that illustrate the wind energy potential across a different region. These maps takes various factors like terrain, topography and a local wind patterns. Next one is wind farm layout and micrositing. Accurate wind resource assessment guides the layout and the placement of wind turbine within a wind farm. Turbines are sited to optimize energy capture while considering the wake effect. This wake is the turbulence generated by the upstream turbine that can affect the downstream turbines. Next one is uncertainty analysis. Wind resource assessment involves addressing uncertainties associated with the collected wind data, and it can be modeled with the help of various techniques such as sensitivity analysis, Monte Carlo simulation and are often employed to assess the impact of these uncertainty on energy production estimate. Next one is validation and calibration. Wind resource assessment are validated and calibrated using historical wind energy production data from existing wind farm. This process helps refine the accuracy of future assessment. Now we will discuss in detail about the advancement in wind energy resource assessment, how this wind energy assessment techniques has been evolved and advanced in the recent past decade. Advancements in wind energy resource assessment technique lead to more accurate estimates of the available wind resource in a specific location. This accuracy is crucial for determining the feasibility of wind energy project and optimizing their design for maximum energy production. Accurate wind resource assessment enables turbine manufacturers to design the turbine that are specifically tailored to the wind condition of a particular site. This optimization can lead to increased energy capture and improved turbine performance. Accurate assessment of wind resource also helps in avoiding costly mistakes such as building wind farms in low wind areas. This lead to better allocation of resources and ultimately reduces the overall cost of wind energy project. Now, the traditionally or old assessment techniques consist of instrument like cup anemometer, wind vanes. These are mounted on tall mast and are used for measurements of wind speed and wind direction. But this high mast or a meteorological mast only provides a point measurement and are unable to provide a volume measurement. It is one of the major disadvantage of a meteorological mast. These meteorological masts have an inherent complexity and a cost issues. The wind energy sector is moving towards the installation of wind turbine in hilly, forested, complex and mountainous terrain. Now we can see that India is moving towards the installation of wind turbine in the offshore sites. The modern wind turbines are gaining heights and their sizes are generally with the diameters of 60 to 110 meter of blade diameter and are further attached to their hub heights at the height of 70 to 100 meter. As the turbine height increases, correspondingly meteorological mast instrumentations, erection and its maintenance become expensive and very difficult. Therefore, the wind industry is moving toward the alternative state of art techniques and instrument to conduct measurement at higher heights and at complex terrain. This challenge can be overcome with the help of an advanced techniques which is known as a remote sensing techniques. The remote sensing techniques, for example, SODAR, sound detection and ranging, and LIDAR, light detection and ranging, can be used as an alternative technique to measure wind speed and direction due to their ability to correctly measure the wind speed at higher heights and at complex and hilly terrain. Because of its portability, that means it can be moved from one place to another place, whereas in cup anemometer or a metallurgical mass techniques, it is fixed. It cannot be moved from one place to another place, but in case of remote sensing techniques, it is portable in nature. It can be moved from one place to another place. It also has an advantage that it measure a 3-dimension scanning capability and has also encouraged its deployment and popularity in wind energy industry. This remote sensing techniques serves platform for real and measure the downstream wind velocity. The remote sensing techniques can be utilized for determining complete wind field structure, including mean wind speed, turbulence profile, time series wind data, and the wind shear profile over a blade. It is a more quantitative and accurate remote sensing techniques. The more quantitative and accurate remote sensing techniques for wind energy application includes SODAR, LiDAR, and a satellite based sea surface wave scattrometry. SODAR stands for sound detection and ranging, LiDAR stands for light detection and ranging. Sound detection and ranging and light detection ranging includes wave propagation and a backscatter detection based device. SODAR is based on probing the atmosphere by sound propagation. LiDAR, light detection and ranging, is based on probing the atmosphere by electromagnetic radiation or microwaves or laser light, and satellite remote sensing is based on microwave scattrometry on the sea surface. SODAR and LiDAR are performing the direct measurement of wind speed based on Doppler shift, whereas the satellite scattrometry are based on proxy empirical calibration methods. SODARs have been used intermittently in wind energy application. The LiDAR, on the other hand, is a most recent development which had complication in the past with cost, size, cooling and eye safety. However, all such problems have been offset with the development of the technology. Now, we will look SODAR and LiDAR one by one. First, we will discuss SODAR. SODAR stands for sonic detection and ranging or sound detection and ranging. It is a remote sensing technology used in various applications including wind energy. In wind energy, SODAR systems are employed to gather information about vertical wind profile, which is valuable for wind resource assessment, wind turbine microsighting and optimization of wind farm. SODAR plays a crucial role in wind energy application by providing detailed vertical wind profile, optimizing turbine placement and layout. It also assists in assessment of wind resource and contribute to the operational efficiency of wind farms. It is an essential tool for harnessing the potential of wind energy and maximizing its contribution to the renewable energy mix. SODAR devices are employed to assess the wind resource at a potential wind farm sites. These devices use sound waves to measure wind speed and direction at different heights or altitude above the ground. Sonar system typically consists of multiple microphones that emits sound chips vertically into the atmosphere. By measuring the time it takes for the sound waves to be reflected back by the atmospheric turbulence, sonar can determine wind speed profile up to the several hundred meters above the ground. It also measures the vertical wind profile of the wind speed and direction, which is important in understanding how wind condition changes with height and altitude. This information helps in identifying the optimal hub height for wind turbines within a wind farm. Different altitudes can have different wind speeds, and selecting the right hub height can maximize energy capture. Sonar data assist in determining the optimal layout of wind turbine within a wind farm. By understanding the vertical wind profile, a developer can arrange turbines to minimize wake effect, where one turbine's wake affect the performance of downstream turbine. Sonar are also used to create detailed wind resource map that show the wind speed and direction at different heights above the ground across a specific area. This maps helps in visualizing the wind energy potential and variability within a region. Sonar measurements helps in micrositing, which involves selecting precise location for individual turbine within a wind farm. By considering the vertical wind profile, terrain and wake effect, turbine can be positioned optimally for maximum energy production. It can also be used in the operation and maintenance of existing wind farms. By continuously monitoring wind condition at different heights, operator can adjust turbine settings to match changing wind profiles, improving the efficiency and the lifespan of the turbine. Sonar measurement can be used to validate and calibrate the data collected from meteorological tower or other remote sensing technologies like LiDAR, SAR or spectrometry. This helps ensure the accuracy and reliability of a wind resource assessment. Sonar is particularly useful for offshore wind energy project, where assessing and maintaining meteorological tower can be challenging. As India is progressing towards the development of offshore wind power plant, so sonar, LiDAR or the remote sensing technique can be a fruitful for the assessment of wind resource. Sonar systems mounted on platform can provide valuable wind data for designing, operating and maintaining offshore wind farms. The data measured from sonar can contribute to short term and long term wind forecasting, allowing wind farm operators to anticipate changes in wind condition and optimize energy production and grid integration. Recently, sonar technology continues to evolve, and leading to the improvements in accuracy and its usability. Research efforts are focusing on enhancing the technology's ability to capture complex atmospheric phenomena and provide even more accurate wind data by using SODAR. LiDAR. LiDAR stands for light detection and ranging. It is also a remote sensing technology similar to the SODAR, which is used to record a wind characteristics, that is wind speed, wind direction at different altitudes and at different heights. It is also portable in nature, that means it can be transported from one place to another place. LiDAR uses a laser light to measure distance and create a detailed 3D maps of the environment. In context of wind energy, LiDAR technology has found various applications for wind resource assessment, turbine performance optimization and operational monitoring in both onshore and offshore wind farms. LiDAR devices can be deployed on meteorological mast or on a stand-alone platform to measure wind characteristics above the ground. LiDAR provides accurate and comprehensive wind speed and direction, enabling the creation of detailed vertical wind profile. This data is crucial for assessing the wind resource potential of a site, including variations with altitude. Here altitude is height. Traditional meteorological tower have a limitation in capturing wind data at higher altitudes. Wherever I am using the term altitudes, it clearly shows the height. LiDAR technology allows for accurate measurement at hub height and beyond the hub height, which is essential for optimizing the placement of turbine and determining the most suitable hub height for maximum energy capture. LiDAR data helps in optimizing the layout and placement of wind turbines within a wind farm. By analyzing wind patterns and wake effect, developer can strategically position the turbines to minimize the impact of one turbine's wakes on the performance of neighboring or nearby turbines. Data measured by LiDAR assists in designing the overall layout of wind farm by considering factors such as terrain, topography and wind condition. This ensures that turbines are situated in locations that provide optimal energy production and operational efficiency. LiDAR data can be used to create high resolution wind resource map that depict wind speed and direction across a specific area. This map offers a valuable insight into the spatial distribution of wind energy potential. LiDAR technology is particularly valuable for offshore wind farm, where installing a traditional meteorological mast, or we can say a conventional technique, or we can say a high lattice tower equipped with all the instrument and sensor is challenging and expensive. Floating LiDAR units placed on platform provide accurate wind data for offshore wind resource assessment and operational monitoring. For operational monitoring, LiDAR device can be installed on individual wind turbines also to continuously monitor their performance. By tracking changes in wind condition and turbine behavior, operators can optimize energy production, predict maintenance needs and extend the lifespan of the wind turbines. For the wind turbine control, LiDAR can be integrated into the wind turbine control system to adjust turbine setting in real time based on this detected wind condition. This enables turbines to operate efficiently and safely in varying wind regimes. Some advanced LiDAR system uses multiple units, with one acting as a reference and other as a measurement device. This approach can enhance data accuracy and provides redundancy. For data validation and calibration, LiDAR measurement is used to validate and calibrate data from other remote sensing technologies and other meteorological tower to ensure the accuracy of wind resource assessment. In case of forecasting, LiDAR can contribute for the forecasting of short term and long term wind, helping wind farm operator in making informed decision about wind energy production and grid integration. Thank you.